Okay, let's begin by solving first a kinetic problem. So we're going to look at a 200-pound block that's being pushed by a force P at that angle of 30 degrees, and the coefficient of friction, kinetic friction, is 0.25. Let's find the force P required to accelerate the block at 10 feet per second squared to the right. First thing I'm going to do is draw a free body diagram to represent what is going on. I'm going to put on the left of this equation, well, on my free body diagram, I'm going to put vectors for the external loadings, like the weight, which is 200 pounds. There's a force P here. We have the ground pushing back up with a normal that isn't necessarily in line with that 200 pounds, and we have friction holding us back. And this friction is a function, of course, of the normal force, which is equal to 0.25 times the normal. For my kinetic diagram, I'm just going to have mass times the acceleration. I'm going to predict the acceleration in this direction. That's the direction we're pushing. So let us sum forces in the x direction. And let's figure out all the forces going on here in the x direction. We're going to have a component of P in the x direction minus the normal force. Let's put an F here so we don't confuse that for a Newton. And this equals essentially the mass, which is 200 over 32.2. And if we were to work that out, that comes out to be 6.21 slugs, or pound seconds squared per foot. And we need to multiply that by our acceleration, which is given in this problem, 10 feet per second squared. And because the acceleration is given, we're able to solve this just purely with kinetics. Okay, let's sum forces in the y direction. And we get n again, minus this time the y component of p sine of 30 degrees, minus our weight, which is 200. And this equals 0. We have no acceleration in the y direction. So we see here in this problem that we have P here and P here and n, two unknowns in two equations. We have all the other values. We can solve this simultaneously and get a result. And that result is P equals 151 pounds. Okay, so let's add some kinematics to our problem. And this is example 13.2. So we're going to fire a projectile into the air at some height h. In addition to gravity, there is a force of drag from the wind, and that is equal to 0.01 velocity squared. What height do we reach with that velocity? So let's draw our free body diagram again for this ball. On it we have a force of drag here, 0.01 velocity squared. We also have the weight of this cannonball. I forgot the cannonball has a given weight. So this has a mass of 10 kilograms, so we've got 10 kilograms times 9.81 for the weight. There's also another parameter I forgot to add. This thing launches at a velocity of 50 meters per second. Our kinetics here then, I'm going to draw as mass times acceleration down. So that's going to reverse our, essentially, make down positive here in our problem. And we can choose this any way we want, so long as we're consistent in our equation of motion. That means then that first off, we have the drag on the left side. It's positive because I'm drawing it down. And then we add to that our weight. And we set this equal to our mass, which is 10 times our acceleration. Dividing both sides by mass, we end up with a relationship for our acceleration here. I'll go ahead and box this, although it's not really an end result. Okay, so let's use kinematics to determine our height. Here, the relationship we want to use is acceleration equals v dv dz. Now remember, this is positive, and our datum is the edge of the cannon here that we fire from. Well, our acceleration relationship we solved above is v squared plus 9.81. Again, this equals v dv over ds. So the problem we need to solve, separation of variables here, is this. Let's not use a ds here, let's use a dz. And we're going to go from 0, our datum line, to minus h because we're going in the negative direction. This equals the integral of velocity divided by, we're going to bring this relationship for our acceleration over here because it has a v in it when we do our integration. And again, we end at 0 for our velocity, but we start at, we're going to start at minus 50 meters per second because, again, I'm going in the opposite direction from the way I drew my line. The integration on the right you can solve by setting the denominator equal to u and use u substitution up here, and we'll end up with this relationship down here for h, and we can solve then for h in this relationship is 114 meters. So that's how you would use kinematics in combination with kinetics to solve a problem.